Oh, hi guys, Mr. Janowski here. This is part 5, I believe, of the chapter 13 slides for astronomy. In the last part, we learned about the magnitude system where you compare the different brightnesses of stars, and we learned about apparent magnitude versus absolute magnitude. The first one's related to brightness, the second one's related to luminosity, so remember the difference between those two. In this part, we're going to talk about the spectra of stars and how two very important early heroes, early female heroes in astronomy, discovered important things using that. So let's get started. And we're loading. All right, so think back to many chapters ago when we first started learning about spectra. What are the three types of spectra we dealt with? They are continuous spectrum, where all of the lines are there. It's just a continuous, complete rainbow. There's also emission line spectra, where most of the spectrum is missing, and you only get the lines at specific wavelengths. And then finally, there's absorption line spectra. It should be spectrums. Anyhow, absorption line spectra, where most of the spectrum is there, but specific wavelengths are missing. So if you're looking at stars, what type of spectra do most stars have? It's the bottom type. Most of the light is there, but specific wavelengths are missing. When we did the thing with the green carousel, we got the emission line. Stars usually give you this. More on why you get that in a couple of slides. So you can learn a lot by looking at a star's spectrum. You can learn its composition, meaning what elements are there, its temperature, meaning if this is the spectrum, okay, well, here's the peak here, so plug in Wien's law, and it tells you the temperature of the thing. Its luminosity, that gets complicated. We'll see how that works. Velocity and rotational speed, you figure these things out using the Doppler effect. So we learned way back in chapter 4 why stars tend to produce this absorption line spectrum. The reason is the star itself is very, very dense. So the body of the star tends to produce, it basically acts like a black body, and it gives you a continuous spectrum. However, all of that light has to shine through the much cooler atmosphere above the star. So the cooler atmosphere actually ends up, it's emitting its own light, but most of what it's doing is deleting the light that's coming from beneath it. So it ends up deleting the wavelengths corresponding to the things that are there, to the elements and molecules that are there. So yeah, different atoms have different energy levels, so they have different differences between their energy levels, so they emit and absorb light at different wavelengths. So yeah, this is what spectroscopy is. Hydrogen absorbs at these wavelengths. Gas is calcium. If you heat calcium enough so that you vaporize it, it emits at these wavelengths. So from the absorption lines that you find, you can figure out what the star is made of. And if you get really clever, you can even figure out, well, how much of each of the relative things are there. Not just that there's hydrogen and there's helium and there's calcium and there's other things, but what's the relative proportion of those things there? So temperature is going to have a big effect on this. So remember that the lines of the star spectrum, be they emission or absorption lines, correspond to jumps from specific energy levels to other ones. So you can have the element in the star's atmosphere, but if the atmosphere is the wrong temperature, you're not going to see the absorption line from that thing. It gets kind of tricky why that is. So let's talk about that. So yeah, real quick vocab term, the Balmer series. Hydrogen has any jump down to the second level in hydrogen produces visible light. I'm sorry, not any jump, but several jumps down to the second energy level produces visible light. And that's called the Balmer series after the name of the person who discovered this. So, I'm sorry, these are not jumps down. These are actually jumps up. Jumps from the second level up to a higher level. So if you're going from 2 to 3, it's going to absorb this wavelength, the red one. If you're going from 2 to 4, it will absorb this one. From 2 to 5, it will absorb this one. So the key is you need to have hydrogen atoms that have electrons in their second energy level already for this to happen. You can't jump from 2 to 3 or 2 to 4 or 2 to 5 if you're not in 2 to begin with. So if the star is too hot or too cold, you're not going to have many electrons in the second energy level. So if the star is too cold, cold relative to other stars, most of the electrons are going to be down in the first energy level. And if it jumps from the first level to any other level, it absorbs a wavelength, but not invisible light, so it won't produce the Balmer series. If, on the other hand, the star is too hot, it's got so much energy in it that most of the electrons are going to be in the third or the fourth or the fifth energy level already, or they might just be completely ionized, ripped off of the hydrogen atoms. In that case, nothing's jumping from 2 to 3 or 2 to 4 or 2 to 5 because nothing's in 2. Everything's already in 3, 4, 5, or higher. So if you have either of these cases, you're going to have very, very weak hydrogen absorption lines. So it turns out that only when the star is in this temperature range, between about 8,000 Kelvin and 15,000 Kelvin, will you have enough atoms with electrons in the second level. If it's cooler than 8,000, too many of the electrons are in the first level. If it's hotter than 15,000, too many of the electrons are in the third or fourth or fifth level to begin with, and not enough for starting in 2 to jump up to another level. So you don't see those Balmer absorption lines. So once you take all of that into account, it gets very complicated, obviously, and figure out what the stars are actually made of and how much of those things there actually, of each of the elements there actually are, it turns out that stars are mostly like what the sun is, which is 71% hydrogen, 27% helium. So add those two together, you get 98%, and only about 2% everything else. And this was a huge surprise. We'll get to the person in this part who figured this out for the first time, and it was so surprising that her advisors didn't actually believe her. A bit of controversy over that. At the time, before she discovered this stuff, people assumed that, well, the stars, they formed out of the same cloud of gas as the Earth, we think. We still think that. So they're probably made out of the same things as the Earth in about the same proportions as the Earth. That's what everyone thought. Turns out that was very, very wrong. So here's this picture real quick. Trying to go quicker. I want to keep these videos relatively short. Brief history. Early 1800s, Joseph Fraunhofer discovered dark lines in the spectrum of the sun and later discovered similar lines in other stars. So we discovered these lines. Joseph Fraunhofer discovered them. These lines in the spectra of the sun and other stars a long time before we had any idea what they actually meant. We knew they were there. We could find repeating patterns in different stars. We just had no idea what they actually meant. So years later, Italian priest and scientist Pietro Angelo Secchi found a connection between the patterns that he was observing and the colors of the stars. Then a little while after that, a doctor, Henry Draper, who was an amateur astronomer, began actually photographing things. So we've seen this photo before, this particular photo. This is Henry Draper. This big box back here is actually a camera taking images on a big glass plate. And this part here is a telescope. So he was taking images of these spectra, an important pioneer in that. And then he died very young. I think he was younger than I am. I think he was less than 40 when he died. And his widow, they were very wealthy. She endowed a bunch of money to Harvard to create this whole compilation of stellar spectra, kind of in memory of her husband. I forget the widow's name. She was involved in this work too. She knew what was going on. She wasn't just a socialite. She was studying this stuff and had thought of taking this whole project on by herself. Ended up not doing that because basically she had other things to do. So she turned all of her husband's equipment and this idea over to other observatories, and in particular Harvard. And she gave Harvard a bunch of money so that they would start this program to record all of the spectra that they could. So when they first started doing this, they came up with this system based on the strength of the lines, and they classified them in 17 different categories, starting with A, going all the way down through Q. So this system once had 17 different categories, and they were in order A through Q. Keep that in mind because it's about to get weird. But first, I read all about this. I know most of this stuff, but over the summer I read this book called The Glass Universe. If you're looking for early female heroes in STEM, this would be a very good book. Turns out at Harvard they hired a bunch of women to do this. They called them computers, was their job title, to analyze all of these spectra. There were a few reasons for that. One is this was fairly tedious work. It was fairly low paying, and so the important menfolk at the astronomy thought it beneath them to actually do this work. So they hired women who they could pay less, and the women did this. Now, the upshot of that is these women got really good at this data because they were dealing with it constantly, and many of them made very important contributions because, yeah, they were knee deep in this data. They knew this stuff very, very well. And a couple of early heroes in astronomy in this. We'll talk about two of them today. There's another one, Henrietta Swan-Leavitt, who we're not going to talk about. But yeah, we'll talk about two of these very important women at the Harvard Observatory in the late 1800s, early 1900s. So the first one is Annie Jump Cannon. So she was working on the catalog. She was starting with that original 17 category A through Q system, and she realized this is not a good system. There are actually too many categories. Most of them are kind of duplicates, and they're in the wrong order. So she couldn't just start from scratch and just redo the whole thing because too many stars had been cataloged already in the old system. But what she basically did is she reorganized it, put the groups together, trimmed it down from 17 categories and down to 7, and then put them in order according to their temperature, which is related to their color. That's Wien's law. Their temperature is related to their color. So her system has them in this order: O, B, A, F, G, K, M. In the system, O's are the hottest and M's are the coolest. So why do we have this sloppy system using letters and they're all out of order? It's because we started with a alphabetically sensible system that ended up not being the right way to do it. So yeah, we kind of had to mix. She improved the system. So how are we going to remember this very bizarre system of letters? Annie Jump Cannon herself came up with a very handy mnemonic for it. The mnemonic is "Oh, be a fine girl, kiss me." She wrote "Oh, be a fine girl, kiss me." If you prefer, you can make it "Oh, be a fine guy, kiss me." In her career, so she was doing this for a very long time. So look at this picture, a younger Annie Jump Cannon. Now we have a much older Annie Jump Cannon. She classified more than 350,000 stars. That's a lot of stars. So yeah, what she was doing is looking at glass plates like you see in this photo here with a little magnifying glass and going star by star, looking at its spectrum and putting it into different classes and naming it. Seems kind of tedious, but she made important contributions based on being willing to do that tedious work. So I'll put a link to this song. This song is terrible, but you have a right to hear it. And then this other video, this one's not so terrible. You might like this one. At least it's not a horrible song. I'll put a link to that one too. So quick review. Who was it that simplified the system of stellar classification? It was Annie Jump Cannon, OBAFGKM. And generations of astronomy students have learned a particular mnemonic for remembering this, and that mnemonic is, "Oh, be a fine girl, kiss me." Okay, I should have gotten rid of this slide. Okay, now to another hero in this story. She worked at the same time, but kind of a little bit later too, than Annie Jump Cannon, was Cecilia Payne-Gaposchkin. So, the spectral types are based on the appearance. These categories are based on the appearance of the spectrum. So, A stars have very strong hydrogen lines. B stars have helium lines, but weaker hydrogen lines, and so forth. There's different rules for all the different categories. So we knew this. We knew it was related to temperature, but nobody knew the nuts and bolts of this until Cecilia Payne-Gaposchkin figured this out in the early 1920s. So she's a very interesting character in herself. Hey, read that book, Glass Universe. It tells you all about her. There was a different astronomer, an Indian astronomer named Meghnad Saha. So he did some quantum physics, quantum mechanics, figured out how the temperature of the thing would affect where the electrons would be for each different element. So Gaposchkin took his work and used it to show the very correct and reasonable order of Annie Jump Cannon's system. So, yeah, you can watch this video too. This is an interesting one. Of the two, Cecilia Payne-Gaposchkin is, at least to my view, the more important. She made a greater discovery. She's the one who figured out that stars aren't made of the same stuff in the same quantity that the Earth is. Again, everyone thought, well, the crust of the Earth is mostly oxygen, and we know there's a lot of carbon and other heavy minerals here. So astronomers at the time had guessed that stars are made of the same thing. So when she was doing her work, she figured out, much to everyone's surprise, that it's actually hydrogen is far and away the most common things you find in stars. Atomic element number 1 is 70-some% of stars, and almost all of what's left is atomic element number 2, helium. And everyone was surprised at that. And in the video, she explains it, but she kind of glosses it. I mean, not Cecilia Payne-Gaposchkin, she's now dead. She's not explaining it, but the woman hosting the video explains it. But she kind of glosses over some of the things. Basically, she wanted to publish this in her thesis, and her advisor, not to be evil, he really had her best interest in mind, thought that result was too crazy. He didn't believe it. And so he convinced her not to emphasize those results. She still had those results in there, but she kind of downplayed them. She said, we think this is a spurious result, but this is what the data are. Then a few years later, her own advisor, through his own work, realized that she was right. And to his credit, when he published his results, he said, oh, and I'm not the first person to come up with this. It was actually my student several years ago who came up with this idea. His last name was Russell. William Norris Russell, William Russell, whatever his name was. But anyhow, when he realized that she was right and published his results, he said, no, she was the first one to get this. And then unfortunately, the scientific community at the time said, way to go, Russell. Congratulations on your wonderful idea. So she got kind of the short shrift. Anyhow, I'm sure this video is getting too long. In this video, in the SciShow, I feel like she glosses over that fact in a way that makes her advisor look like a jerk. Her advisor wasn't actually a jerk. He thought her results were crazy, and then when he realized her results were right, he said so. He did the right thing. It's just unfortunate that he got all the credit for this, and she should have gotten a lot more. So, quick review, because this video is getting long. What are the 3 types of spectra that we have? We have continuous emission line and absorption line, and most stars have absorption line spectra. So of these 2 famous women at the Harvard Observatory around 1900 and later, who was it that simplified the 17-letter classification scheme down to 7 letters and reordered them according to "Oh, be a fine girl, kiss me"? That was Annie Jump Cannon, who classified 350,000 stars over her 40-year career. And who was the other great astronomer? Well, one of the other great astronomers, there were several, who discovered the physical basis of this system. It was Cecilia Payne-Gaposchkin. So again, read that book and watch that video on YouTube. You'll like Cecilia Payne-Gaposchkin especially. Very important hero in STEM. And the thing she figured out, that stars are 70% hydrogen and 27 or 28% helium, is a huge key to understanding the universe, really. And it's great evidence for the Big Bang and later things that come. So yeah, I'm really impressed and kind of marvel at what it would have been like to be the first person to kind of have that key to how the universe works, how to figure that out. So yeah, I'm hugely impressed by her. And hopefully you are too. So I hope you found that interesting.